Hey everyone, today I'm going to see how well I perform at a Meta phone interview. So, this is the Lead Code premium feature. So you can go into Lead Code and pretty much go into interview here and assessment. And all the FANG companies are pretty much here. And yeah, there's like, I'm just going to click into this Meta. There's online assessment, phone interview, and on-site. So let's see how I would perform in a Meta phone interview. Let's just run this. So each session will include up to 3 questions, and I'll have an hour and 30 minutes to complete all questions. Once the mock assessment begins, you cannot pause the timer. Cool. Let's just start this. Given two integer arrays, nums1, return an array of their intersection. Each element the result must be unique, and you may return the result in any order. So return an array of their intersection. So the intersection here is 2. Intersection here intersection here is like 4 and 9 because 4 and 9 exist here. So what I'm thinking is we parse one of the nums into a set, and then we go through the other number because we have to look through each of these elements. So we convert one of the arrays into a set, and then we go through the other numbers, and if there's a collision, we add that to like a result set as well, and then we basically convert the result set into a list before we return the result. That will give us unique result. So we're given a result. We'll say result is a set, and before we return, we'll turn like the result into a list. But we're gonna take nums1, and then we're gonna turn it into a set. I mean, we can just convert both of them to a set and do a set intersection. So let's not make this any more complicated than it needs to be. We'll say nums1 set equals, you just turn nums1 to a set, nums2 set equals set with nums2, and then intersection. You could probably one line this, but I don't want to make it too I don't want to do any crazy syntax. Let's say nums intersection. So you take the intersection of these two sets, and that'll give us like return us another set. And yeah, we take nums1, we turn that in set, and then we take nums2, turn that into set, and we take the intersection of two sets, it returns us another set, which is the intersection, and we just need to turn that into a list. Let's just see if that works. Let's see if it works on this. This should return like no intersection. This should return us 4 and 9. Okay, cool. Nice, that worked. Let's move on to the next question. So given the root of a binary tree, the depth of each node is the shortest distance to the root. Return the smallest subtree that it contains. Given a root of a binary tree, the depth of each node is the shortest distance to the root. Return the smallest subtree such that it contains all the deepest nodes in the original tree. Interesting. A node is called the deepest if it has the largest depth possible among any of the nodes. Interesting. Okay, this one's kind of... The subtree of a node is a tree consisting of a node plus... So let me read this again. We're given the root of a binary tree. The depth of each node is the shortest distance to the root. Return the smallest subtree such that it contains all the deepest nodes. So we just need to figure out all the deepest nodes. Pretend it was here. Okay, that gets interesting. It's kind of like a lowest common ancestor question. of the deepest nodes. Given the root, the depth of each node is the shortest distance. Return the smallest subtree such that it contains all of the deepest nodes in the original tree. A node is called the deepest if it has the largest depth possible among any node in the entire tree. Let's see. Yeah, I think it's similar to the lowest common ancestor question. So I think all we need to do is figure out two nodes that are the deepest and then find the longest common ancestor between these two nodes. If it's only one node that's the deepest, pretty much just return its parent. So let's see. How are we gonna do this? I think we can. What I'm gonna do is like I'm gonna find. Pass. Let's see. This is actually a pretty good question. We won't Excala draw this, so we can just like quickly write it out here. What we're gonna do is like find two of the deepest elements, and once we do that, we're gonna do find the lowest common ancestor of these two elements. So given the root of the depth of each node, yeah, because pretend we had something like this, or pretend we had something like essentially, if we had something like this, where are we? The result would actually be this guy, I'm pretty sure. Because the deepest nodes are here. So we need a subtree that contains all of those. So we have to find the lowest common ancestor, which is this node, and return that as the root of the subtree. Okay, that's a good question. So what I'm going to do is I'm going to find the deepest nodes. If we only have like one of the deepest nodes, we can literally just return that node, I think. Yeah. Otherwise, we'll do the lowest common ancestor thing. So where are we now? We're going for speed here. So let's see. Let's find the deepest nodes. And to do that, we can use like a level order traversal or something. Self root. So we're going to do a level order traversal to find the deepest nodes. So we're going to start with we're going to do a level order traversal. So we're going to take our DQ. We're going to start with the root. And since it's a tree, we don't need to worry about like a scene array or anything like that. We're going to say we're given a root. And then we'll say while length of the queue is greater than 0. We're going to do some algorithm. And then we're going to do result equals. Like, how do we return the lowest level? We'll make a hash map, levels equals like this. And then we'll say, or we can just do a map here. And what we can do is like return levels -1. That'll return like the very last level. And what we're gonna do is we're gonna do a level order traversal. So for in range, the length of the queue, what we're gonna do is we're gonna say candidate equals queue.pop left. That's going to get us this, and we're going to do q dot append pop left. We're going to append, we're going to say, what are we going to do here? We need to keep track of our level. So level equals the length of levels. And then we're going to do levels.append. So that's going to like initialize this levels like this, so we can add to it. And we're going to say candidate, we're going to say levels.append. And I have videos on how to do this level order traversal thing. But levels slash level dot append the candidate. So we're going to throw that there. And we're going to go q. We're going to take the q dot append if candidate dot left, then we want to add that to the queue. So we're doing a level order traversal here. I have videos on that too, just look it up. Otherwise this video will take too long. So that will find us the deepest nodes. So let's just do this. Self.find deepest nodes, and we'll give the root. Print then we'll say for node in deepest nodes, print node.value. We're just gonna try to see if this algorithm is working the way we want it to. So we're seeing like it's given 7.4 here, which makes sense. So we'll say if the length of deepest nodes we'll catch if root is none, return root. That just captures the case if root is none there. And then we have another edge case. If the length of deepest nodes is equal to 1, just literally return deepest nodes dot zeroth. Because that's like this case. Like we only have like one. If we only have one element, that's the deepest node. Just literally return that. Otherwise, we just need to access two of the deepest nodes and find the lowest common ancestor. Wait, is that gonna work? Wait, no, that's hard to, let's see how we're gonna do that. Because that won't work, because the lowest common ancestor, if we pick these two nodes, are not going to be it. So essentially what we need to do, do we need to like go upwards on the tree to find, like we need to, like now we have all the deepest nodes. We just need to be able to find out how they connect. Because pretend they're here. How would we do this? We basically need to find the lowest common ancestor of all nodes and not just two nodes. Because if we find this one, we'll return this, but the result is actually that. So that's a bit off. So what I'm thinking is we might need to like traverse up the parents until all of the parents are equal. Well, that's hard. There must be an easier way to do this. Like, we need to know the lowest common ancestor of each of these parents. So I think one way to do it is capture all of the parents. Let's see, but if there's a parent here, We don't want it to we want it to return this one and not that one. Let's see. Let me think about this for a second. Can we do like a post order traversal? Can we do a post order traversal in which we return the one, like we do a post order traversal and we return the result on, like we count up the number of these nodes that have been seen. So what we could essentially do is we can create a set of all of the deepest nodes. We could do a post order traversal. So when we're looking at a node, we ask the question like, have I seen all of the other deepest nodes already? If I did, yeah, essentially we do a post order traversal, and every time we see a node that's the deepest that we have, we like increment the count, and the first one to hit the target. So pretend if we have 3, the first one to hit the, like it won't, like here it would count 2, and then here it would count like 1, and then finally it will join here, 2 plus 1 equals 3. The first one to return that would be the result. So, okay, that's gonna work, I think. Doing a post order traversal here. Let me just lower this. So let's just implement this here. So we have our deepest nodes. We should probably want to turn this into a set. Then we'll do a post order. We'll be given like a node. We'll be given like a target, and then we'll also be given like a set of our deepest nodes. If node is none, just return. Then we're doing a post order. That means like look left. Or what's going on here? Left, right, then look at myself. It's like if, okay, left. So we're basically gonna say like if left equals self dot post order left, or node dot left, and then right is equal to self dot post order node dot right. If left plus right is actually equal to the target, we want to return, or we're gonna set some result. And this is getting complicated, and I can like clean this up after, but let's just get this working. Self dot result equals none, and after we're gonna do our post order. We're gonna do return self dot result. We're gonna do our post order here. Self dot post order of root. The target equals the length of the deepest nodes here, and then we also want to return the deepest nodes. So if the left plus right is equal to target, and self.res is actually equal to none still, what we're gonna do is essentially we're gonna just keep we're gonna self.res equals this node. That means that's our actual result, and we're just gonna keep letting this thing run. And then what we're gonna do is return left plus right. It's like if But I need to, like, if I am actually one of these, I need to return +1. So like if this node is in the deepest nodes, then I'll return left plus right +1. So I can walk this through in a sec. I'm just itching to submit that. Does that work? Set is not superscriptable. List. Let's see if this works. Okay. Boom. Finish session. Didn't catch that one edge case, so nice. Finished it in 20 minutes. In 21 seconds, even like the time allotted was 1 hour, 30 minutes. Now let's like look at our score report and see how we perform against like other people who did this and other meta interviewers. How are people solving this? BFS. Yeah. Let's see. So your interview score of 7 beats 79% of all users. Not too happy with that. You can see the last time I did any of these was 8 months ago. So I could improve my performance a bit. How do you actually solve this? I'm not sure if I'm allowed to share editorials. So I'm going to leave it as that. That was my solution. Yeah, pretty much that's a meta phone interview for you. You should try this out if you have that feature. But yeah, thanks for watching. I'm gonna do other meta, or I'll do other ones, or let's see how it goes. Or what can we see here? This, I like this thing. It's kind of interesting. It's like after you do all this, you can do a review and you could see how you perform against other people who work at those companies. So cool. See y'all in the next video.